In this video, we'll conclude our discussion of historical numeration systems by talking about a positional system and the Babylonian numeration system. So in a positional system, instead of writing the multiplier with another number to multiply it by, like a power of 10, we just write the multiplier alone. The number to multiply it by is understood from that multiplier's position. All right, that's a bit of a mouthful, but here's the gist. We just looked at the Chinese numeration system. So for a number like 364, they would have written this 3 hundreds, 6 tens, and either 4 ones or without that one. Okay. Now that's very close to the way that we write numerals. We just don't include these hundreds and tens, and we also don't include the ones. They're not needed because we understand from the position where in the number these digits are what their value is. All right, so the Chinese system, it was written top to bottom like this, and it can be confusing. It almost seems like it is a positional system because the position of the numbers matters, but it's not positional because where the place of the 3 is doesn't tell you what its value is. It needs this number with it, this 100, to tell you what that 3 represents. So that final jump to the most advanced numeration system is recognizing that we don't need those extra numbers with the multipliers. So ours is the Hindu-Arabic system, and ours is positional. We don't use the tally system, obviously. We don't use simple grouping. That was like the Egyptian system, where they would write hieroglyphs over and over. So, in the tally system, the number 40, or like 42 or something, that would be 42 tallies over and over and over again. All right, that's the tally system. In simple grouping, they would have had to write 4 of whatever symbol they chose for tens, and 2 of whatever symbol they chose for ones. In multiplicative grouping, we would have had to write 4, and then a symbol for 10, and then 2, and then maybe a symbol for 1, depending on the system. So it's still quite a bit of information to write. But in the positional system, we just write 2 symbols, 4, 2. So this is the most concise way to write this, and definitely the most advanced. Now, in order to use a positional system, there has to be some understanding of exponents. We've used these it's been implied with the tens. All right, we talked about thousands and hundreds, tens, ones, etc. But all of these are actually powers of 10. So here's a quick review of what we mean by exponents. If you see something like b to the n, all right, that's an exponential expression. And that base number, the b, represents the what number is used as a factor, and then the exponent, the n, tells you how many times to write that number. Okay, so we have a base and an exponent. So for example, if we had 3 to the 4th, that would tell you to use 3 as a factor 4 times. And as a factor, we mean part of a product, so we're multiplying here. Right, so exponents show shortened multiplication. Then we have 2 that we define. Anything to the first power is just the number itself, so we're using it once. And then anything to the 0th power, we define to be the number 1. Okay, as long as it's not like 0 to the 0th. That's a weird case that we don't define. Alright, so notice if we go back and look at the place values that we're using, we're grouping by tens. And so 1,000, that's actually 10 to the 3rd power. 100 is 10 squared. And then we have 10, which is 10 to the 1st. And then 1, if you use this definition of 0 exponents, that could be written as 10 to the 0th. So here's kind of an expanded place value chart, and of course this isn't all of them, but this is some of the lower place values up to the billions. Okay, we have ones, tens, hundreds, thousands, 10,000s, 100,000s, and then the millions, and then billions. Okay, so a quick review. In the number 153,946, what is the place value of each digit? And if you read it in words like that, it's almost apparent from that. Okay, so the place value, we'll just do a few of these. The place value of this 3, all right, well that's in the 4th place. Okay, 1, 2, 3, 4. That's in the thousands place. So the place value of the 3 is the thousands. All right, and then how about this 4? 4 is in the tens place, so its place value is 10. Okay, so place value is basically what we mean when we talk about that number that's missing from after the multiplier. Okay, so I don't write 4 and then the symbol for 10. That 10 is implied. That's the place value. Expanded notation is just a way to write a numeral so that it makes it obvious what those place values are. Now we definitely use tens and we also use exponents in this notation. So first thing you do is break this down by place value and write everything out. So the 3 is really 30,000, the 2 represents 2,000, 5 is 500, 6 is 60, and 9 is just 9. Then we separate out the multiplier from the power of 10. So this is 3 times 10,000, 2 times 1,000, 5 times 100, 6 times 10, and 9. We don't usually write times 1, but you could if you wanted to. And then finally, the last step to make this truly expanded form, we want to emphasize the fact that these are all powers of 10, so we write them with tens and exponents instead. Okay? And just as a review, remember that if you're trying to find the exponent, it matches the number of zeros. So 10,000 has 4 zeros, and that's why it's 10 to the 4th. Okay. And you can see this is why we call this a base 10 system. Right? All of these are based on place values, which are groups of tens and powers of tens. Okay, so let's write this number in expanded notation. So first I'm going to separate out everything into its place values. All right, so 9 is in the millions place. Oops. All right, and I'm going to write 9 times a million right away. Okay, and then plus. Now I have 0, 100,000s, plus 3 10,000s, plus 4 thousands, plus 7 hundreds, plus 6 tens, plus 3, and then you can write times 1 or you can just leave it as 3. Alright, now this is not the final answer, but it does help us to see what the powers of 10 should be. So this is 9 times 10, and then I count 6 zeros in a million, so this is times 10 to the 6th. 0 times 10 to the 5th. 3 times 10 to the 4th. 4 times 10 to the 3rd. 7 times 10 squared. 6 times 10 to the 1st, or you can just write 10 plus 3. Okay, so this final one, this is expanded form. Okay, this is useful when we go to look at the Babylonian numeration system. Theirs is a positional system, but they didn't group by 10, so that's what makes this one a little bit interesting. It's also cross with a simple grouping system. It's not truly a positional system, but you'll see elements of both of these as we go through. They use cuneiform, and these were markings on clay tablets made by a stylus, and depending on how they held the stylus, whether it was the end or tilted a little bit, you can get these two shaped symbols here. One kind of looks like a triangle or like a maybe like a boomerang, and then this one's a little bit like an upside down skinny triangle. All right, I'm going to simplify these, and I'm just going to write them like this. All right, since I don't have a stylus like they would have used, but hopefully you'll understand which symbols I mean when I write those. The picture here is an example of some early clay tablets, and these may have been student tablets. The instructor would have written some sort of an example problem or a homework problem on one side, and then the student would write the answer out on the back, and then that would be their homework that they would turn in. Alright, values for these symbols. This first one represented 10, and this second one represented 1. And these were the only two symbols that they had in this numeration system. So what number does this represent? All right, so it's simple grouping for numbers 1 through 59, and you'll see what happens after that. But to start out with, we just look at the value for the symbols, and we add everything up, just like in the Egyptian system. So this would be 3 10s, followed by 6 1s, so this represents 36. Okay, 1 through 59 were written using those two symbols, but after the number 60, a space was left between groups of numbers, and they started grouping by 60s. All right, so why 60s? Some may think that this has something to do with time. They did more accurately look at time in terms of, hours and minutes and things like that. They also broke down degrees, right, and circles into degrees. So if you think about the expression a 360-degree turn, the Babylonians would have used a similar system to that to break down circles into 360 degrees. And they also broke down degrees into what we call minutes and seconds. So it is similar to time. So when we look at the Babylonian system, it's similar to thinking about time. So we'll use that for this example, 2,538, to kind of understand how this works. All right, so first of all, this is larger than 59, so they would have started thinking of this as kind of like minutes and seconds. All right, minutes and seconds. So let's ignore this example for now and just think of this in terms of time. Let's say you had 2,538 seconds. How would you turn that into minutes and seconds? Well, the first thing I would do, I know that there are 60 seconds in a minute, so I would try to find out how many groups of 60 are in this number. Right? And the way to find groups of something is to divide. So if you divide this by 60, okay, and use a calculator if you like, and this gives 42.3. So that tells me that there are 42 groups of 60, or in other words, 42 minutes, and then I have this remainder that represents some seconds left over. All right. Now, calculators give remainders in decimal form, and I'm interested in a whole number. I want to know how many whole seconds. So if we do 42 minutes times 60 seconds, all right, 42 times 60, that tells me how many seconds are in 42 minutes. Right, that's 2,520. And then if I subtract that from the original amount, okay, 2,538 seconds minus 2,520 seconds, that tells me that there are 18 seconds left over that weren't enough to make a whole minute. Okay, so now let's look at the Babylonian symbols that you see here. And notice that this first grouping, these are their symbols for 42, and here, these are their symbols for 18. Right? So it's almost like looking at 42 groups of 60 seconds. All right, this is 42 times 60. And then the second group represents ones, so this is kind of like looking at seconds, 18 seconds. Now we can expand on this idea, and if we see three groups of numbers, they would represent groups of 3,600, 60, and 1. All right, why 3,600? Well, that would be similar to hours. Okay, how many minutes are an hour? In an hour, 60. Okay, so if you had 60 seconds, or let's go the other way, 3,600 seconds. Okay, if you divide that by 60, that tells you how many minutes there are, so that's 60 minutes. Okay. And 60 minutes is 1 hour. Okay, so 3,600 seconds, that's kind of like looking at hours, and then 60 is minutes, and 1s is seconds. Okay, if this still feels unclear, don't worry, we'll do some more examples to see how this works. Alright, so first of all, write the number represented. This is example 3. So notice this big space here between the groups of symbols, and that's our clue that they're representing 60s here. and then here they're representing ones. Okay, so I would count up the symbols first, and I see symbols for 5 tens and 2 ones first of all. Okay, so that's 52. And then in the second grouping, I see symbols for 3 tens and 4 ones, or 34. All right, now those first 52, that's 52, and that's counting how many groups of 60, so I multiply. And on the second, that's 34 ones. And then we add to put everything together. Okay, so 52 times 60 is 3,120. And then plus 34 ones, so this is the number 3,154. All right, let's try this one. There are 2 spaces, so this numeral is counting groups of 3,600, then it's counting 60s, and then it's counting ones. Okay, so the first symbols represent 12, that's 1 10 and 2 ones. Okay, so that's 12 groups of 3,600. And the second, there's symbols for 5 tens and 1 1, so 51, and that's counting groups of 60s. And then finally, groups of ones, there are 23 ones. And then we add to combine all of those things together. All right, so 12 groups of 3,600 is 43,200. And then 51 groups of 60 is 3,060. And then plus 23 ones. And altogether that is 46,283. Okay, let's try going the other direction. Write 5,217 using Babylonian numeration system. So first of all, I want to look at groups of 3,600 and see how many of those I can make. Then I want to see how many groups of 60 I can get out of this number. And then how many groups of 1 are left over that can't make 60s and 3,600s. Okay, so division is the way to go to find how many groups. You might also try subtraction if you can see right away that there's one group of 3,600. If you didn't, then I would suggest division. All right, so first of all, 5,217 divided by 3,600. And using a calculator, that's 1.449 ... etc. Okay, so we're interested in the whole number part. We have enough to make one group of 3,600, and then this decimal part represents what's left over. All right, so I'm going to subtract that one group of 3,600 to see what's left. And that's 1,617. Okay, now that number, I want to see how many groups of 60 are in that, so divide by 60. And we get 26.95. So there are enough to make 26 groups of 60 with some left over. All right, now it's tempting to say that there are 95 ones left over, but that the decimal doesn't represent a whole number, so I need to figure out what that actually is, how many ones. So what I want to do is take 26 groups of 60 and subtract that. So I had 16, 17, and I want to subtract 26 groups of 60 and see what's left. All right, well, 26 groups of 60 is 1,560. And subtracting that from 16, 17, and that gives 57. All right, so there are 57 ones left over. Now, if it helps you to think of this in time, then maybe try this on your own as a check. See if 5,217 seconds is 1 hour, 26 minutes, and 57 seconds. Okay, so work through that arithmetic and try to convince yourself. Now the last thing we need to do is just write this using the cuneiform symbols. All right, and we're going to use that using these symbols here. Okay, so one group of 3,600, we just need a symbol for 1. 26 is 2 10s and 6 1s. Okay, and then we have 5 10s and 7 1s. And then sometimes you can stack like this too, so if it gets too long to write all in a big line. But what needs to be there, make sure that your spaces are really obvious to show that you're transitioning to the next group of 60s or 1s, something like that. Okay, let's try another example. How about 120? All right, groups of 3,600, groups of 60, groups of 1. Well, I don't have enough to make groups of 3,600, so that tells me that I'm only going to need 2 groups of symbols. So the first thing we look at is groups of 60, and there are 2 groups of 60 in 120. Okay, you can find that again by dividing, and this is exactly 2. There is no remainder, so there are 0 1s left over. Now the Babylonians didn't have a symbol for 0. They would have just kind of left that blank. All right, so this would be written with the symbol for 2 1s, and that's it. They would have relied on context as a way to clue them in as to which number this was, but you can see why this was confusing and why developing a 0 was certainly an advantage and was necessary as calculations and counting became more complicated. All right, how about 7,200? So same thing, let's look at groups of 3,600, groups of 60, and groups of 1s. And if you divide this, okay, 7,200 divided by 3,600, and again, that's exactly 2. Okay, so 2 groups of 3,600. Sorry, that's a little messy there. Divided by 3,600 is 2. So that means that there are 0 60s and 0 1s. Alright, so again, this would have also just been written with the 2 symbols, alright, for 1s. And then let's look at one more example which needs a little bit of work to figure this out. 14,653. So groups of 3,600, groups of 60, groups of 1s. Alright, so first of all, divide 4,653 divided by 3,600. All right, and let's see, that would be 4.07 ... etc. It keeps going. All right, so that's 4 groups of 3,600. All right, so what I want to do is take 4,653 and subtract 4 groups of 3,600. Okay, so 4 times 3,600 is 14,400, and subtracting is 253. Okay. Now as a check, that should be smaller than 3,600. If it's larger, then that tells you there's enough to make another group of 3,600. All right, next divide that by 60 to see how many groups of 60 are in there. And that's 4.21 ... Okay, so 4 groups of 60, that's 240. So subtract 240. Okay, and that gives 13 left over, 13 1s. And then finally, we need to write this using Babylonian symbols. So we have 4 1s, then a space, then 4 1s again, and then a 10 and a 1. Alright, so that's a look at the Babylonian numeration system. You can see that it's similar to ours and that there's place value. Alright, by putting some spaces in there, it's indicating when they're switching from ones to 60s to 3600s. Now that's similar to ours. We would switch from ones to tens to hundreds, but it is a little bit different than ours in that there is some grouping within each of these digits, and the reason that that's needed is because their digits go over, they need more than one symbol to show those digits. So for ours, we don't need more than one digit to show 9. We have a symbol for that. Alright, so that gives you a brief look at the history of numeration systems, and in the next section we will look at different base number systems, which is a different way of recording numbers, still using Hindu-Arabic numerals, but grouping by something other than tens.